Okay, we've all been there, right? You're trying to buy something online, and you're just staring at this wall of ratings. It seems simple at first, but the more you look, the trickier it gets. So let's actually dive into this, because there is some really fascinating math hiding behind what seems like a simple choice.
So let's put you in the driver's seat for a second. You found a product you need, and there are 3 different sellers offering it for basically the same price. The only thing you have to go on are their user reviews. So the question is, which one do you trust with your money?
All right, here's the data. Seller number 1 has a perfect 100% positive rating, but it's only from 10 reviews. Then you've got seller number 2, a little lower at 96%, but with a more solid 50 reviews. And finally, seller 3 is at 93%, but they have a whopping 200 reviews. You know that perfect score from seller 1 is so tempting, but with only 10 reviews, it feels kind of risky, doesn't it? This is the classic dilemma. A higher score versus more evidence. How in the world do you make a rational choice here?
Now, before we get our hands dirty with the more complicated math, I want to show you a really neat shortcut. It's this wonderfully simple trick that actually gives us a clear winner. Think of it as a little preview of what's to come.
It's a thing called Laplace's rule of succession, and honestly, it couldn't be easier. For any seller, you just pretend they had 2 extra reviews, 1 positive and 1 negative. So for our seller number 1, instead of 10 positive out of 10, we imagine it's 11 positive reviews out of a new total of 12. And then you just recalculate the score. That's it.
So, what happens when we do this for all 3 sellers? Well, seller 1's perfect score drops to about 92%. Seller 3 barely budges, landing right around 93%. But seller number 2, they actually come out on top with a new score of 94.2%. See, what this rule does is it gives a little penalty to sellers with fewer reviews, kind of acknowledging that there's more uncertainty there. So according to this nifty rule, seller 2 is your best bet. But why does a trick like this even work? To really get that, we need to go a bit deeper.
Okay, so the real problem here, the reason this is tricky at all, is that we're dealing with a huge unknown. We can see the reviews that have been left, but what we can't see is each seller's true, underlying chance of giving a customer a good experience. We'll just call this their true success rate.
And this is what makes our shopping problem so different from a textbook example like, say, flipping a coin. With a coin, we know the probability. It's 50-50, end of story. But with the seller, that 96% rating isn't the final answer. It's just the evidence we have so far. We have no idea what that seller's actual score would be if they had 1 million reviews, and that uncertainty is the whole game.
And really, that's the heart of it. A seller who is, in reality, a 95% true success seller could easily get 10 out of 10 positive reviews just by random chance. In fact, that happens about 60% of the time. The data we see is just one snapshot, one possible outcome. The whole challenge is that we just don't know the real number.
So how do we start to handle this kind of uncertainty? We need a tool. And our first tool is a real cornerstone of probability theory. It's called the binomial distribution. This is going to help us model the situation and start making sense of all this.
So what is this thing? Well, to put it simply, the binomial distribution helps us figure out the odds of getting a specific number of successes, in our case, positive reviews, in a fixed number of attempts. You know, it's the math that powers things like repeated coin flips, or in our case, repeated customer experiences.
Okay, let's zoom in on seller number 2 and see how this actually works. We saw 48 positive reviews out of 50. To figure out how likely that result is, we can use a formula that's basically just asking 3 simple questions. Now don't get hung up on the symbols here, the ideas behind them are what's important. So here are those 3 questions. First, how many different ways could those 2 negative reviews have been scattered among the 50 total reviews? Second, what are the odds of getting 48 positive reviews in a row? And third, what are the odds of getting those 2 negative ones? You multiply those 3 answers together, and that gives you the final likelihood. Okay. Now that we have this tool, we can do something really cool. We can start testing out different hypothetical success rates and see which one makes the data we actually have, that 48 out of 50, the most likely. Let's just visualize it. It'll make it super clear.
So let's play a what-if game. What if the seller's true success rate was only 90%? Well, if that were the case, the chance of us seeing 48 positive reviews out of 50 is actually tiny. As you can see on this chart, it's super unlikely. So a 90% true success rate, it just doesn't seem to fit the data we saw.
But what if we guess that the true rate is 96%, exactly what our data says? Well, bam, the likelihood just shoots up to its peak. And that makes perfect sense, right?
The data we observed is going to be most probable when our hypothetical true rate is a perfect match for it.
And just to check, what if we try a really high success rate, like 99%? Well, look at that. The likelihood drops back down again. Why? Because a seller who is that good would be much less likely to have even 2 negative reviews. So our data starts to look improbable again.
So the big takeaway here is this. The data we actually saw, 48 out of 50, is most likely to happen if the seller's true hidden success rate is 96%. This peak value is what statisticians call the maximum likelihood estimate. It's just a guess that makes our evidence make the most sense. But hang on, we're not quite done. There is one more subtle but absolutely critical twist to this story.
We've figured out what success rate makes our data the most likely. But it turns out that isn't the question we actually want to answer. We need to flip our entire way of thinking around one last time.
Take a close look at this because it's so important. What we've calculated so far is the probability of seeing our data given we assume a certain success rate. But what we really want to know is the reverse. What's the probability that the seller has a certain success rate given the data that we've already seen? They sound similar, but believe me, they are not the same thing at all.
So that's the key question, isn't it? We have a way to calculate the odds of the evidence, given the theory. But how do we flip that whole equation around to find the odds of the theory, given the evidence? Answering that is the final piece of our puzzle.
Well, the tool that lets us make this incredible flip is one of the most elegant and frankly most powerful ideas in all of statistics, Bayes' rule. It is the magic key that lets us turn what we know into a clear statement about what we don't. And how it does that? Well, that's a story for next time.